And hello, welcome everyone. I'm just going to continue where we left off the last video. In the last video, we saw that one of these, what do you call it? The root finding algorithms, they were kind of bugged. Um, and I had to spend some time figuring out where the bug was. And for the very astute observer, those of you who are sharper, you would have realized that I forgot to add a cosine right here in my previous videos. And that has contributed to the roots being very strange values. Okay, so now after I added this cosine term in, in the course of debugging, I did it off off the record so that you don't have to what you do not have to watch as I try to figure things out, because I think I've done quite a lot of that already. Okay, well, after I did this, I found that some of the roots, the values actually match pretty closely. Some of them are a little bit more off. Let me explain. So we have the roots here according to Wolfram Alpha, or even using Scilab or GNU Octave. Okay, the roots are minus 3.0489 for this equation, x cubed minus 7x plus 7. The roots are minus 3.0489, 1.6920, and 1.3569. Now, if you take a look at these roots and you compare it to the roots here, we have 3.0 minus 3.048, almost 9. 1.6920, okay, that's there, but the second root here is 1.7575. Now that is kind of close to 1.6920, but not as close as I'd like. I'd like it to be less than 1% error at least, that kind of thing. And the last root over here is 1.3569, but over here we have 1.2853. So what could be wrong over here? Okay, so that we're gonna have to spend some time figuring this out as well. So my guess for the time being is that the constant conversion between degrees and radians in a very imprecise manner, that is the problem. So what do I mean by that? What do I mean by that? So you can see here that I'm using a dimensioned phi over here, and phi is the arc cosine of q squared by 4, and you divide that by the minus p cubed by 57. That is right here. Okay, p and q are listed here, and phi here is q squared by 4 divided by minus p cubed by 27. Now that's all well and good, but the thing is that phi here is likely going to be in radians. Okay, when you do an arc cosine or something, it will give you back a radian value. Okay, return value is in radians in the range 0 to pi. It is not a number if this arc cosine is outside the range -1 and 1. Okay, so this is the arc cosine. So I will get an answer in radians, but I converted it into a degree. Okay, I converted it into a degree before plugging it into this formula or this function, get yk. Now get yk gets phi in degrees, but once again, to use the cosine value, I convert it back to radians. Okay, I converted it back to radians. So you can see here I need to do a 5 by 3 plus 120k. 5 degrees by 3 plus 120k. So there's 120 times k as f64. I converted it to radians using pi over 180. That is standard. Pi divided by 180. And then I had to do a cosine. So my guess is that, well, as we had this problem, as we do this conversion back and forth, then we sort of have to account for all of these all of these things. Okay, the whole conversion thing. So 5 degrees has to be converted to a radian value. Okay, so I have to convert this whole angle, right? 5 by 3 plus 120k. Okay, 5 by 3 plus 120k, that is the angle I have to convert to radians. So phi here is in radians, phi here is in degrees, excuse me. Then I needed to convert it to radians. And then 120k also needs to be converted to radians. So I want to skip the step of converting from degrees to radian and back, because I suspect that that actually impedes the accuracy of this. Yeah, I suspect that impedes the accuracy. So let's do something about that. Let's try to do away with this inaccuracy thing. So let's see. I'm going to change this. Okay, I'm gonna copy this whole thing, rather copy this whole chunk here, and I'll paste it here. And I want to call this get yk radians. Okay. And what I'll do here is I will change this to phi in radians. Okay. So right, I'm going to have phi in radians here. So what happens here is that I do not need to convert this 5 radians divided by 3 into a radian value. So I'm going to cut this part out. Okay. All right, so the only part I do conversion is this part, right? 120k times pi over 180. So I'm going to do that for all three. It down, I'll go here. Okay. See, so there are 3 values here. I'm going to change this down, and this will be pi divided by 180. I'm going to leave I'm not going to convert it into a simpler fraction, because I want to okay, what am I converting to simpler fraction? Okay, 120 divided by 180 is technically 2 over 3. I could change it to 2 over 3, but I want to leave it as a 120 over 180. Okay, and 120 being the degrees here, and 180 being this degree conversion into radians. So I want to leave it right there. Okay, I want to leave it there because it makes the code easier to debug. Now I'm going to get this yk in radians right here. I'm going to get this yk in radians. Okay, I'm going to put this here. Phi radians equals phi dimension, and I'm going to change this to radian. And I'm going to try and quick fix this, because this is going to, of course, give an error. Okay, I'm not quite done yet. Yeah. So and instead of doing this, instead of cancelling it, alright, I'm going to just modify this over here. I'm going to change this to get yk radians. I'm going to change this to phi radians. Okay, paste it here and paste it here. Okay, let's see whether the situation improves. Okay, so when I change it to radians, okay, I get 3 of the same answers, which is not exactly what I intend. Okay, because the k is equals to 0 in all cases, I need to change it to k equals to 1 and k equals to 2. So I'm going to change it as such, k equals to 1 and 2. And hopefully I'll get something a bit closer. Unfortunately, okay, so that theory failed. That theory failed. I do have 1.7575 and 1.2853 right here. So apparently this error is not due to um it is not due to the, let's see. Yeah, it's not due to the degree and radian conversion. So this must be some other problem. Okay, maybe well, I guess I'll come back later. I want to come back later. And I want to just implement the second test first, which is this polynomial here. X cubed plus 8x squared minus 7x plus 9. So I'm going to have 8x squared here minus 7x, and I'm going to put plus 9. And then I'll have the solution right here. Okay. Okay. Now I'm going to do only have one real root. Okay, I'm going to just put the second test first. So one good thing, one thing I like to do is to actually pick the lowest hanging fruit, so to speak. So for tests that are easier to pass, let's just write them down first. So in the course of programming, I will usually like to make sure I get the easy parts done first. That will kind of sort of give you some sort of motivation to continue. At least there is some small success. That's better than having many failures in a row. So that's just one strategy for coding a lot. Okay, now so when you do one real root, what do you get here? Minus 8.9001. And lo and behold, the real root here is minus 8.9001. Okay, that's the only real root we have. Okay, so if we have one real root, what should that root be? Okay, the root should be minus 8.9001. Okay, and the thing is that I do not want to use this panic to try and get what the root is. Okay, I want to use an assert equal, right? Assert equal. Assert. Okay, assert equal. I'm going to put the solution. I'm going to get the first element of the solution, which is usually 0, and I put minus 8.9001. So that is how I'm going to do it. Unfortunately, that's going to have an error because you actually have to get these floats to the last decimal point in order to make sure they're exactly equal. So let me show you what I mean. I'm going to take out this panic. Okay, still going to fail 2 tests. Okay, what's this over here? Yes, one of the tests failed. You see that the one real root test, okay, this test failed because the left is not equals to the right. So what's the left thing? The left is the solution. Okay, this is the left right here. The solution. This solution matrix only has this solution vector, excuse me, only has one so-called one element, and the first element is at index number 0. Index number 0 is minus 8.900, 1, 2, 4, 6, so on and so forth. And what's on the right is minus 8.9001. Now these are almost equal but not exactly equal. So we cannot use this assert equal unless we go and copy down all of these decimal points. Though I don't really want to do that, but yeah, I don't really want to do that. So it's not bad. Yeah, I don't really want to do that. So how are we going to get this thing done? How do we account for this almost equal, right? So that's where this assume approx equal comes in. Okay, I'm not sure whether I've done it before, but I just assume I have not. Okay, so assert equal actually tries to ascertain or check exactly whether these two values match. Okay, in this case it is solution, the first element of the solution, index 0. That's why I use the square bracket 0. That gets the first element in this vector. Okay, it starts from 0, it does not start from 1. Okay, most of the time when it comes to programming, we start with index 0 rather than index 1. Okay, and then on the right side, we have something we want to compare it to, which is minus 8.9001. Okay, so what should we do right here? Okay, so instead of asserting that these two are exactly equal, I want to assert that these are almost equal. So the macro I use is assert relative equal. Assert relative equal, which is right here. Assert relative equal. So what does assert relative equals do? Okay, it basically checks whether these two numbers here are almost equal within some tolerance. Okay, tolerance. So what's the tolerance here? Okay, eps. Okay, let's try eps equals 0.01. So I'm doing so will let's see, epsilon. Right, epsilon, not eps. Epsilon equals 0.01. Okay, what's epsilon here? This is the approx relative. Okay, epsilon here actually is an error term. It's usually an error term. So it's a fractional error. It's a relative error. That means if let's say I'm trying to compare these two values and I want to check whether they match within a fractional error of 0.01. In other words, do they match within 1%? Then I'll use epsilon equals 0.01 because 0.01 is 1%. Okay, I can actually change this. Let me write a comment here. Epsilon is the relative error, fractional error. Okay. Okay, and okay, so if it is 1%, then okay, if my error tolerance is 1%, then epsilon equals 0.01, so on and so forth. Yeah, I should get what I'm saying. So let's say I want a 0.01%. Okay, then I can just use epsilon equals 0.001. Okay, so this is equivalent to an error tolerance of 0.1%. Let's just say this is satisfactory for this code, and that is fine. Now you can see over here that the one railroad test has passed. Okay, so that's just saying that hey, this code works for finding one railroad. Okay, but we still have to find this three railroads answer. Okay, so we discussed that maybe this what do you call that? We discussed that maybe this formula, this formula, if it's correct, no, not this formula. The problem may not come from the constant conversion back and forth between radians and degrees. So we saw that in debugging. Okay, so to test that, I tried to code another function that takes phi in radians so that I don't convert between radian and degrees back and forth as many times. The only time I convert from degrees to radians is using this 120k times pi over 180. Okay, so that's the only time I will convert between degrees and radians. Okay, unfortunately, that does not really help. Yeah, that does not really help here. So the conjecture is that hey, the error must be something else, right? The error must be something else. Okay, so yeah, if the error is something else, then yeah, we there are only a few possibilities. Okay. Okay, so I wanted to eliminate whether the degree to radian conversion was a problem. I've just found out that that's not. So maybe one other possibility is that this formula here is there's something a little off with it. Maybe it is not accurate enough. Maybe it's an approximation. I don't really know. because we see the roots are pretty close, but not that close, maybe within 10% of the real roots that we saw just now. So we'll need to sort of think of some other way. Maybe there's some other formula that actually fits this right here. Fits this yk. Actually gets yk for us, which is okay. But at least this formula here, this complex roots and one real root formula, this formula here seems to work. Okay, this formula here seems to work. So that's at least half the code tested. So yeah, this is what we have to do during debugging. We have to sort of eliminate what are the possible causes of error. So so we move on to our next course. We have figured out maybe that the conversion, it may not be the error. Now, is it the thing that, you know, did I get this formula wrong? Right? You can verify for yourself here that the formula should be more or less equals to what I typed here. Right? It's the same as what I typed here, unless what I typed here is wrong. Okay, and for that I need to go and check Paris Chemical Engineering Handbook again, or some other resource. Okay, maybe I typed it wrong. Maybe the last one is well, maybe these formulas are so approximate that they don't really give you the actual value. Maybe the formula for cubic root finding is even more complicated, and this is just a simple approximate form. So let's check it out. Okay, so I checked with Paris Chemical Engineering Handbook. So in case, well, it seems that the formula was copied over correctly, but well, there's this last point of discrepancy which I see here is the 120K degree. Is this in a degree or radian? So just now over here, I assume right here that it was a degree. Well, maybe it's not a degree, maybe it's a radian. So I'm going to try taking the radian thingy out. Okay, I'm going to take this one pi divided by 180 out to convert this from degrees to radians, or yeah, to convert this from degrees to radians. So I'm going to take this out. Okay, and that's the thing about units. It's always good to specify the units explicitly. So let's check out what the values are. Let's check out what the values are this time. Okay, minus 3.042. Okay. Minus 2.319, and well, what do you have here? Minus 0.733. So this is even further from what we had before. In fact, what we have over here, the 3.042, this seems even further from, yeah, this seems even further from the what we had before. 3489. Okay, so let's undo that and let's check the answers again. Okay. Yeah, these answers seem to be better. Okay, I do not know why this is giving these answers. Maybe let's check for other sources of error. Okay, I rechecked the handbook, and I think I might have copied this formula wrongly. The formula here should be a square root. This phi here, this q squared by 4 over minus p cubed by 27, this should be square rooted. Okay, this should be square rooted. So let me do this square root, and let's see whether that solves the problem. And the yk here, let's see about getting phi right. Okay, phi radians is here. Phi radians is here. Phi. Yeah. So before I do the arc cosine, I need to square root the thing first. Okay. And let's check the numbers this time. Ah, perfect. Minus 3.04891, 1.69, and 1.35. So that seems to be the formula which now I copied over wrongly. So now we have a working cubic root finding algorithm. Not perfect, but I mean not very neat, but at least you know the code works. We have tested it. So I'm gonna kind of stop for now, but at least let me change the documentation here to put the square root on this 5. Okay, so that's the thing. So at least going through all this debugging helps, and I had to pause the recording process, and you know refer a few times back and forth from Paris Chemical Engineering Handbook, but more or less the formula works. So let me add this square root in. Okay, this is the real gases.pdf file. So let's go to the real gases.type and put this here. Let's give this real gases.pdf where k equals all of this, and the cosine inverse or yes. So this is fine. I need to square root these numbers. So let me just quickly add a square root sign here. SQRT. Okay, there we go. I need that square root over here. Now with the square root in place, we kind of have the correct ingredients for these roots. Okay, we have the correct ingredients for these roots, and well, I want to of course automate the test, but I'm not going to do it in this video. So I guess I will see you next time. And we have also figured out that yes, indeed, this 120K here, it is this whole formula here is in a degrees. Yeah, you have to change all of this into degrees. Okay, 5 is in degrees, 120K is in degrees. So that's the mystery that has been solved. Okay, so let me commit this is cubic equations more or less working. Commit this to GitHub. Sync, and see you next time.